So our next topic is magnetic field intensity due to coaxial conductor. So in coaxial conductor, this is the cross section view of the coaxial conductor. So we know that in the coaxial cable we are having the two conductors, one is inner conductor and another is outer conductor. So the inner conductor is having a current plus I and the radius is A, and the outer conductor, this is the outer conductor which is having a radius B. But this outer conductor is having some thickness, and this thickness is, suppose this one is this thickness, I denote it by suppose T. So because of this thickness, which is for the because of this thickness, the radius of this outer conductor has been increased, and now it is C. And in this conductor, because of the thickness of the conductor, the current is flowing in the minus I direction. So in the conductor, in the coaxial conductor, in one conductor the current flow in the positive direction, and in other conductor the current flows in the negative direction. So this is plus I and this is minus I. Now by Ampere's law we have to find the magnetic field intensity, and the magnetic field intensity in the different cases we have to consider, because we have already calculated the magnetic field intensity due to the single conductor of finite radius. It is a two conductor of the finite radius. So case 1, if we consider the case 1, when our point of interest say rho is greater than C, this is the first case. That means we are going to calculate the magnetic field intensity outside this coaxial conductor. So suppose if I want to calculate this magnetic field intensity at this point P, this is the first case, and by the Ampere's law, so according to the Ampere's law, integration over the closed loop H dot dl is equal to the current enclosed. So at this point P, to make the closed loop, I will draw this circle. This is the cross sectional view, right? So we know that this circular loop is nothing but a Amperian path. If this is the conductor, single conductor, and if we want to find at this point, so we will make this closed loop, because the magnetic field will be present around this particular circle or in this loop. So this is the conductor and the magnetic field is around this conductor. So integration over the closed loop H dot dl is equal to current enclosed. Now because we have told that this is the current in the inner conductor which is plus I, and in the outer conductor it is minus I. So the total current enclosed by this Amperian path is plus I minus I. So this Amperian path will enclose the two current, which is plus I and minus I, sum of the positive current and the negative current. So the total will be 0. So integration over H dot dl will be 0, and hence we can say that the magnetic field will be 0. So outside the coaxial conductor the magnetic field will be 0. This is our first case. Now let's take another case, case 2, when our point of interest is in the thickness of the outer conductor, that is greater than B and less than C, that is in the thickness. Now we are going to calculate the magnetic field in this thickness portion, in that thick region. So let's draw the diagram for this also. Suppose this is the radius A, inner conductor, this is the radius B, and now we want to calculate in this region. Which is having a radius C. Now we want to calculate the magnetic field at this point P, which is at distance rho. So for this again we will draw the Amperian path. So this is the Amperian path now. So this is the amperian path. The current flowing through this thickness is minus I. Now we can see that, and in this particular inner conductor we know that the current is plus I. Now we know that this is the complete thickness in which the current is flowing. Minus I current is flowing in the complete outer conductor. But when we draw the amperian path, the total current is not enclosed by this amperian path of minus I. The plus I current is completely enclosed, but the some portion of the minus I current is enclosing. So that some portion of the minus I current, that means this one, this part of the current minus I is enclosed by this amperian path. So not the total current is enclosed, few currents are enclosed. So we have seen that in case of the single conductor, if this is the case, when some portion of the current is enclosed, then how do we calculate that current enclosed? So that current enclosed is given by the total current, and the factor total current is multiplied by the factor of desired area divided by the total area. So here it is integration over the closed loop H dot dl is equal to current enclosed. So if I consider the differential length in this amperian path, so the direction of the differential length will be this, and the direction of H will also be tangent to this amperian path. So the direction of H and dl will be same, we have seen that already. So this is H dl cos 0, and how much current this amperian path is enclosing. So this is enclosing the positive I current completely and the some portion of minus I. So plus I and some portion of minus I, that means desired area in which the minus I current is flowing divided by the total area in which minus I current is flowing. So this is multiplied with minus I. Now H dl cos 0. So this is integration over the closed loop H dl, and this is nothing but I plus the desired area in which the current that is enclosed by the amperian path, and the total area in which the minus I current is flowing. So the minus I current is flowing in the total area, that is the area of the outer conductor, and the radius of the outer conductor is pi c to b, pi c square minus pi b square. So area will be pi c square minus pi b square. This is the total area in which the minus I current is flowing. But how much portion is actually enclosed by this amperian path? So it is having this particular distance is rho. So it is having the area, how much? This will be the pi rho square minus of pi b square, and that is multiplied with minus I. So this much current is enclosed. So this is I into 2 pi rho, this H into 2 pi rho, H is constant, so it will be outside the integration, and the circumference of this amperian path is 2 pi rho, and now the I is common in both. So this is 1 minus rho square minus b square divided by c square minus b square. Because of this minus sign, here I have placed minus sign and I have taken I common. So now the value of H will be I upon 2 pi rho. This will be c square minus b square minus rho square plus b square divided by c square minus b square, and this b square and b square will get cancelled. So H is equal to I upon 2 pi rho and c square minus rho square divided by c square minus b square. So this is the magnetic field in the thickness region, where the rho is in between B to C. Now let's calculate when the rho is greater than A and less than B. That means now we are calculating in the middle region between the inner conductor and outer conductor. This is the inner conductor, this is the outer conductor, and I am talking about the point at somewhere in between A to B. So let's draw the diagram for it. Now the C part, the outer thickness of the outer conductor is not required, so I am not drawing it. So we are saying that we have to find at this point P, which is at distance rho. So now if I draw the Empyrean path, so this would be the Empyrean path. Now the current enclosed is plus I only, because the outer conductor thickness we have not considered, because our point of interest is inside this A to B. So we don't need to draw the thickness of this outer conductor. So according to this, if this is the Empyrean path, so total current enclosed is plus I only. There is no portion of minus I which is enclosed. So we will write integration H dot dl is equal to I enclosed, and this will be H into 2 pi rho into current enclosed is I. So H is equal to I upon 2 pi rho. So this is the magnetic field because of third case. That is nothing but a single conductor, and for a single conductor we are calculating the magnetic field outside the conductor, because this is inner conductor only and we are calculating the magnetic field outside this inner conductor. Now the last one, case 4, now we want to calculate inside the inner conductor. So now we want to calculate inside the inner conductor. So let's draw the inner conductor only, that is A, and somewhere here it will be B, but we don't need to draw it actually, because we want to calculate at point P, which is at distance rho and inside the inner conductor. So the plus I current was flowing throughout this inner conductor. Now only this part of the total current is enclosed by this Empyrean path. So there is the total I current is not enclosed now. Some portion of this plus I current is enclosed and the minus I current is not even enclosed. So in this particular case, integration H dot dl, if you will calculate into I enclosed, this is the Ampere's law. So integration over the closed loop H dl cos 0, that will remain same, and the total current I, the desired area divided by total area, desired area in which we want to calculate the current. So we want to calculate in this area only. So that is the shaded portion. So shaded portion is having the radius rho. So this portion is having the area pi rho square, and the total area in which this I current is flowing is pi a square. So when you calculate it, you will get I H into 2 pi rho is equal to pi, and pi will get cancelled, and I rho square upon a square. So finally we get I rho upon 2 pi a square. So these are the 4 different cases in which we can calculate the magnetic field intensity. Now let's draw the diagram. How can we draw the diagram? H versus rho. This is magnetic field, this is rho. Okay. So suppose we want to draw from the rho equal to 0. So rho equal to 0 means you are starting from the center, you are starting from this point. So when you increase the rho up to the A, this will follow the case 4. So whenever the rho is less than A, that means less than A means the less than inner radius, that means we are inside the inner conductor. So this will follow this particular relation, and according to this particular relation, H is directly proportional to rho. That means the H will be increasing linearly. H will be increasing. So we are starting from inside, and when we reach to this particular point, the rho will become A. This rho will become A when this point will reach to this point. This rho will become A. So the rho will become A. So when you put rho equal to A here, I upon 2 pi A you will get. That means when this rho will become A, the value will be I upon 2 pi A. Okay. Now if we move from the inner conductor, if we further increase the value of value of A, and the value of rho will be increasing from A to B. So that means now we are talking about this case A to B, that means we are talking about case 3. So in case 3, this H is inversely proportional to rho. So it will be decreasing non-linearly like this, and it will decrease up to B. As when you start from A and when you reach to the B, so here the value of rho is B, that is the inner surface of the outer conductor, inner surface of outer conductor. This rho will become B, and because the value of B is more, so the value of H is less compared to I upon 2 pi A. Here the value will be I upon 2 pi B, because the value of B is more, so the magnetic field will be less. Now after B, that means the distance is rho is B to C, then it will follow this relation, and when you increase the rho from B, this is the minus sign, that means H is decreasing, and that is also inversely proportional. That means the H is decreasing more sharply than the previous, because rho is increasing. So because of this minus sign, this difference will be less, and this rho is also inversely proportional. So here also rho is increasing, so magnetic field is decreasing from numerator and denominator both. That means it will sharply decrease, and when it reaches to C or outside the C, the magnetic field will be 0. So this will be the plot of magnetic field versus this distance rho. So this is all about the magnetic field intensity due to the coaxial conductor. So how you can apply the Ampere's law to determine the magnetic field intensity, we have seen in two different cases. First one for infinite long, second one a single conductor. Now in fact the third one, because of the coaxial conductor in which there are two conductors, and the fourth one in which we had the infinite sheet, and we will derive a more relation for the two different configurations that is important for electrical students. So next topic is magnetic field intensity due to the solenoid. So this is the solenoid structure. A solenoid is nothing but a long conducting wire made up of many loops packed closely together. So it means that if we form many loops, okay, and we packed it closely together, then it forms a solenoid like inductor, and the magnetic field is towards the center, and on the surface of this conductor, this solenoid, the magnetic field is assumed to be 0. So since you can see that this is the direction of flow of current, and now the current is from the backward side and it is towards the upward side. This is the front face of the solenoid, and this dotted line denotes the backward face of the solenoid. So this is the solenoid, and the current is flowing in this way. This way I have shown. So this is the front face. So this is the backward portion in which the current is flowing. So this current is I, which is flowing from the backward and coming into the front. So this is the backward and front, back, front, and so on. And the current is leaving in this way. Now, since it is forming a loop like this, okay, so since it is forming from the backward to the front, the current is flowing in this way. So that is why the magnetic field is toward this, because when I see from this way, so the loop is having the current in anti-clockwise direction. The current is in this direction, anti-clockwise direction. Okay, so if the current is in anti-clockwise direction in a loop, then we know that the magnetic field will approach towards you. So I can see the north face of the loop, and that's why magnetic field is approaching towards me. So this is the magnetic field H towards me. Okay, if I am looking from here. So, and from back side, this is the south pole. So again the magnetic field is approaching towards the loop. So this is the magnetic field direction. And we have to calculate the magnetic field intensity which is lying in this uniform region or in this solenoid in between the coils or towards the center of the solenoid. So for that we will apply the Ampere's law, and let's represent this. If I cut the loops, if I cut the loop by cross section, suppose if I cut the solenoid like this, then we will get the front face, this is the loop, and I am cutting it through the cross section. So we will get the we can able to see only this part of the conductor. Okay, because this is the way how do we represented it. So it is inside and then coming from here to here, right? So this is the wire, and I have cut it from the cross section. So this portion of the wire we are not able to see. So what we can see is the current is leaving the solenoid from here and entering in this region, leaving from here, entering in this region, leaving from here, entering in this region, leaving from here, entering in this region. So here it is leaving and going inside this. Here it is going inside, so it is represented by cross. Here it is again leaving and going inside, so cross. So this is the cross sectional view, and the magnetic field is lying towards the center, and it is uniform. So towards the surface of the solenoid, here the magnetic fields are 0. Just near to the solenoid, this is the solenoid, just near to the solenoid, the magnetic field is assumed to be 0, because it is assumed to be towards the center, because the loops are packed closely together, so it makes the magnetic field towards the center only. So now to calculate this, because we are having some finite length of the solenoid, so let's take this is the length of the solenoid, which is represented by L. Okay, now we have to apply the Ampere's law. So this is H dot dl, current enclosed. So closed loop, inside this closed loop, we are starting from here, A to B, C and D. So it is A to B, the direction of magnetic field and the length is same. So this is H dl cos 0. B to C, it is H dl cos 90, because this is the direction of magnetic field and this is the direction of differential length. So if this is the direction of differential length, it is making an angle theta is equal to 90 degree. This is the dl, direction of dl. And in between C to D, H dl, we will see what is the value. C to D, you can see this is near to the surface. So this is near to the surface. So H is 0 here. So simple, the H is 0. This is Amperian path, right? So what is this? This is Amperian path. Now D to A, what will be the value of D to A? D to A is again H dl cos 0, cos 90. It is equal to the total current enclosed. So how much current is it is enclosing? So suppose this solenoid is having the n number of turns and each loop is having the current flowing through this is I, and there are n number of turns. So the total current enclosed by this particular Amperian path is n into I. Now this is 0, here H is 0, and cos 90, theta is 90 here, theta is 90 here. So all these will be 0, and we get H integration from A to B dl and n into I. So A to B, the total length A to B is small l and is equal to n into I. So we get magnetic field is n I by L. So magnetic field due to the solenoid is n I by L. Now let's calculate the magnetic field intensity due to toroid. So toroid is nothing but the solenoid structure forming in the circular loop. So if you will form the solenoid in the circular way, so it will be nothing but a toroid. So this is solenoid forming a circular structure like this. So this is the backward portion. So now the magnetic field, because the current is flowing in this way, like this is the current flowing in this way, so the magnetic field will lie in this circular way. The magnetic field will be also circular, because the structure is circular, so magnetic field will be also circular. So this is the direction of magnetic field in the anti-clockwise direction, because the loop is having a current in that way only. So it is, when I look from here, it is, for me, it is anti-clockwise direction. This is the center. Now we want to calculate the magnetic field. Let me draw it solid so that the magnetic field you can see. This is the iron core, you can say. This is wound in iron core, soft iron core. Now the magnetic field is in anti-clockwise direction, and now we want to calculate the magnetic field at point P, which is at distance rho. Okay, so now integration over the closed loop H dot dl is equal to current enclosed, and we want to calculate at point P. So here the direction of H and dl both will remain same again, because this is circular. So if I calculate the direction of dl, that will be in this direction, and the magnetic field will also be in this direction. So the direction of H and the direction of dl both are in same direction. Okay, so both are in same direction. So H dl, the angle between them is cos 0. The total current enclosed, again it is passing through the n number of turns, so this is n into I. And because this small differential length, when we add all this small differential length, that means if we integrate it, I will get the circumference of the circle. So this is H into 2 pi rho into n into equal to n into I. So H is equal to Ni upon 2 pi rho. This is the magnetic field intensity. Because of toroid. So these two results are important for electrical students when you calculate the inductance. There are many times in the exam we will get the inductance of solenoid. So when we will see when we will derive or define the inductance, then you will see how to use this particular result to calculate the inductance. So next topic is magnetic flux density and magnetic flux. So let's define magnetic flux density first. So magnetic flux density is defined as B is equal to mu naught or mu into H, simply mu into H. magnetic flux density is is equal to mu into H, and its unit is Weber per meter square, or you can also use this Tesla. Okay. So I am not going to the derivation of it, or I am not going to the depth of this particular definition, because this is simple result, B is equal to mu H, like D is equal to epsilon E. Now the value of mu you can write here. The value of mu is equal to mu naught into mu r, where mu naught is the value of constant, which is 4 pi into 10 to the power minus 7, and mu r is relative permeability of the medium. Okay. So for non-magnetic you can also write this one. For non-magnetic medium, this mu r is 1. Okay. So mu r will be 1 for non-magnetic medium. So this will be B is equal to mu naught into H. Now let's define the magnetic flux. Same as the electric flux, we will derive the magnetic flux. Magnetic flux, it is defined as or we can say it is a measure of how much magnetic field lines passing through any surface. It is measure of how much magnetic field lines passing through any surface. Suppose we are having a magnetic field lines like this. This is the magnetic field lines, say B. Now we are keeping a surface here like this, as we did in case of electric flux also. Suppose this is the surface and we are keeping this plane or the surface like this. So the field lines, these two field lines will be passing through this. So when the field line pass through the surface, it will generate some flux. Okay. So these field lines which is passing through the surface is generating some flux. So there will be many field lines, we are showing only two lines. There will be infinite field lines which is passing through this particular region. So suppose I want to calculate the flux passing through this particular area, because we are having the big plane, and for this big plane we cannot calculate directly. So for that we are selecting a small differential surface. So here we are selecting a small differential surface, and the direction of the differential surface, we know that if the plane is kept like this, so the direction of the differential surface is normal to the surface. So normal to the surface will be in this direction. So the normal to the surface, that means in this direction. This is the normal to the surface. So this is the normal to the surface, and this is ds. Now this is the field line. Here it is the field line somewhere here. So the angle between the field line and the normal is theta. Okay. So the flux passing through this, ds is d xi is equal to b dot ds. This is the dot product. Now this normal vector, the direction of the differential surface, and the b is having angle theta. So we can write d xi is equal to magnitude of B, ds cos theta. Magnitude of ds is ds and the direction is normal and the angle between these two vectors are theta. Now the total flux passing through the surface would be, you have to integrate it. You have to integrate over the surface d is I. So you have to integrate over the surface b ds cos theta. Angle between them is finite, so b and cos theta will be constant. That will be outside this integration, and this is ds. So when we add this small ds, we will get the complete area of this particular plane. So this will be b cos theta into area. So this is the total flux passing through that particular surface. Now if the suppose field lines are like this is B, and if the surface is kept like this, that means we are keeping the plane or the surface in such a way that all the field lines is passing through this particular surface. So we have kept like this so that all the field lines is passing through this particular surface. If all the field line will pass through the surface, that will generate the maximum flux. Okay. So here we will select the differential surface and the direction of differential surface will be this. So B and ds both are same. We know that when the theta will be, when the cos theta is maximum, when the theta is 0, and when the theta will be 0, when the direction of the differential surface or the direction of the surface and the direction of magnetic field will be same. So here the direction of magnetic field and the direction of ds are same. So that's why it will generate the maximum flux. So what will be the value of flux? So here xi is equal to integration over the surface b dot ds, and this xi is equal to integration over the surface b ds. Angle between these two vectors are 0. So this xi is equal to integration over the surface b ds, or you can write b into area. Now suppose the magnetic field lines are like this and you kept the plane in this way. So in this particular case, this differential surface is having the direction this one ds and the vector b, and the angle between them is now 90 degree. So if you calculate the xi, integration over the surface b dot ds, this is the formula for the flux. This is the fixed formula for the flux, integration over the surface b dot ds. Now according to the angle between these two vectors, we will get the different values of flux. Here integration over the surface b ds cos 90, because the angle between these two is 90, so this will be 0. The flux will be 0. So this is the magnetic flux. Now suppose we are considering one case, we are considering a closed surface. Okay, this is the closed surface. Here we are going to derive very important equation and about the actual fact of the magnetic field. So if it is a closed surface, it is a sphere. Okay, so this is a sphere. You can consider a ball. Okay, so this is the ball, and now I am saying that the magnetic field lines are coming like this. Magnetic field lines are passing through this ball. So here it is a ball, magnetic field lines are passing through this ball. So when it will encounter, suppose it is encountering a board, so it will pass through some area, right? So when this is the ball, when the magnetic field line are passed through this ball, so it will encounter or it will incident on some area. So that small area is suppose ds, differential surface. And this ds, what is the direction of the differential surface in case of sphere? When we draw the Gaussian surface, we know that whenever we draw the Gaussian surface, the direction of the differential surface is normal to the surface. So the normal to the surface will be in this direction. So this is the direction of ds. So because the magnetic field line are passing through this, so there will be some flux. Whenever the magnetic field line will pass through some surface, it will generate a magnetic flux. So it will generate some flux, say xi1. Okay. Similarly, when the magnetic field lines are moving outward through this surface, when it is leaving the surface, when it will be leaving the surface, it will pass through some area, again it will pass through some area. Now this is the direction of ds. Now these two are having the same direction. So this is the direction of magnetic field lines, and this is the angle 180 degree between them. These two are having the same direction, so the angle is 0 here, and the flux is xi2 because it is passing through some area. So this is also give some flux. So the net flux will be the xi1 plus xi2, total flux passing through this, total flux passing through closed surface. Xi1 plus xi2, there is one flux, there is another flux. So this is the B and ds, B ds cos 180 degree, and this is B ds cos 0. If you want to write this as a differential surface, so you can also write like this, because you may get confused that why we are not integrating. So let's write d xi1 and d xi2. So this is d xi1 and d xi2. So this is b ds cos 180 and b ds cos 0. Okay. So this is minus b ds and this is plus b ds. So plus minus 0. So the total flux passing through this closed surface is 0. Whether you because when we take the small surface, then we get the total area, but here we are having this small area, so that's why we are only considering this small area. So this particular example concludes that whenever there will be closed surface, the total flux passing through the closed surface will always be equal to 0. Okay, so it concludes that very important relation, total flux passing through any closed surface is always, very important point, always equal to 0. Total flux passing through the closed surface is always equal to 0. So how can we write this? So integration over the closed surface b dot ds, because when there is a no closed surface, b dot ds will have some value, it depends on the direction of b and ds. But if it is a closed surface integration, then the flux will always be equal to 0. So the total flux passing through the closed surface is always equal to 0. So, and this is called the Maxwell fourth equation in integral form. Now this is the closed surface integration. So we know the divergence theorem. So divergence theorem gives the relationship between closed surface and volume. So if we apply here, we get integration over the volume, divergence of B dV equal to 0. So from here we will get divergence of B equal to 0. This is the differential form. So it is showing the magnetic field are divergenceless or solenoid. Okay, so it is divergenceless. Divergenceless, what does it mean? So total flux passing through the closed surface is 0, or the field line passing through the surface, net field line passing through the surface is 0. How we can understand this particular point? So what is the meaning of this? We can also write the isolated magnetic charge does not exist. Isolated, I am going to tell you, just write it now. Isolated magnetic charge does not exist. As isolated magnetic monopole, we can also write isolated magnetic monopole, or you can say isolated magnetic charge does not exist. Now let's understand this point. Suppose there is a magnet. This is the north pole, this is the south pole. We know that the magnetic field lines from the originate from the north and terminate to the south. So it will generate from the north, and magnetic lines always it forms always a closed loop. So it will start from the north and reaches to the south. Like this. So now if I place a closed surface here, this is the closed surface. This is the closed surface. So you can see that through this particular closed surface, the field lines coming in are 2, and the field lines going out are also 2. So that is nothing but the divergenceless property. We said that the total field lines inward and outward should be same. Then the divergence will be 0. So if you place this closed surface anywhere in this diagram, you will find that the total field lines coming in and coming out are same. That's why this is a divergenceless, because divergence is a measure of how much field line diverges about any point, but it is not diverging. The total field lines inward and outward are same. So that is why this is a divergenceless. So the magnetic field lines are divergenceless. Now we have derived all the 4 equations of Maxwell's in the integral and the differential form. So let's write in the form of the table, because this is very important and you should remember it. Everything about this Maxwell equation you should remember. Okay, so let's write in one place so that you can recall whenever you want directly all the 4 equations. So this is the integral form. Differential form, and how they are derived, that is remarks. So we are having the first equation, integration over the closed surface d dot ds is equal to integration over the volume rho v dv. This is the first Maxwell equation that we have derived, and the differential form of this is divergence of d is equal to rho v. Okay, and for charge free region this rho v is 0, and the remark is this is derived from the Gauss law. Okay. Now the second equation that we derived is integration over the closed loop E dot dl is equal to 0. Okay, and from here we get the conservative nature of electric field, curl of E is equal to 0, and total work done in a closed loop is 0. Okay, now this is the second Maxwell equation, and another Maxwell equation that for the time varying field is E dot dl is equal to integration over the surface minus del b upon del t dot ds, and from here we get the curl of E is equal to minus del b upon del t, and it is Faraday's law. And the third is integration over the closed loop H dot dl is equal to integration jc dot ds, and this is curl of H equal to jc, ये है Ampere's law, and integration over the closed surface B dot ds is 0, that is divergence of B is 0, that is magnetic monopole does not exist. So another form you can write, that is for the time varying field, integration over the closed loop H dot dl is equal to integration over the surface jc plus jd dot ds, and here it is curl of H is equal to jc plus jd for time varying field. Okay, so this is the different Maxwell equation, and this Maxwell equation you should remember, and where the closed surface integration and where the closed loop integration is used, that you have to remember exactly, because in the exam directly the Maxwell equation is asked for the matching. Okay, so there will be a in list 1 there will be given the 4 law and the 4 Maxwell equation. You have to just match the law with the equation. So for that you know about the from where it is derived, and you should exactly remember where the closed surface and the open surface or the closed loop integration is given. Here there are 2 equations in which the closed surface is there, and here it is closed loop. So in this way we have derived all the 4 Maxwell's equations. So next topic is magnetic scalar and vector potential. So in the case of electrostatic, we studied about the potential, but in electrostatic we have only one type of potential, that was scalar. But in magnetostatic we have 2 types of potential, that is a scalar potential as well as vector potential. So let's define the vector potential and the scalar potential, and for that we will use some vector identity that we have discussed in del operator chapter. Okay, so the first vector identity is we know that divergence of curl is 0. We wrote like this, DC equal to 0. So divergence of curl equal to 0, that means divergence of any vector, divergence of curl of any vector is 0. So let us say that vector is V. This is first vector identity. Now the second vector identity, which is Cg equal to 0, that is curl of gradient is 0. So curl of gradient is 0. So here gradient we take always for a scalar quantity. So that is a scalar, that is a vector quantity. Now from the Maxwell equation, because we are studying the magnetostatic, so we will be writing the Maxwell equation that has been derived from in the chapter of Maxwell magnetostatic. So Maxwell equation is, which is derived in magnetostatic. First we derived, that is curl of H equal to J. For static field, curl of H equal to J, and the second is divergence of magnetic field B, magnetic flux density B is 0. So here we can see that we have the curl of H, divergence of curl of H, del cross H, and this we can compare with this term. You can compare this, suppose equation number 1, 2, and this is 3 and 4. So if we want to compare these two equations, so we can compare equation number 2 and 3. So comparing equation 2 and 3, what we get is the vector H equal to divergence of gradient of V. So this is the left hand side. If we compare the left hand side, this will be H, vector H equal to gradient of V, and in the right hand side J should be 0. So this equation will be true if J is 0. Okay. So in case of electrostatic, we have studied that the electric field intensity is equal to minus of gradient of V. So here V is the potential, this is the potential, and this is the field intensity, electric field. So similarly, if we compare with this, that means this is now a magnetic scalar potential, because this is a scalar quantity, we take gradient only for the scalar quantity. So this is the magnetic scalar potential, and here also we had a minus sign, so here it is also minus sign. Okay, so this is the way how you can write the magnetic scalar potential. So this is a magnetic scalar potential. Vm is magnetic scalar potential. So it is defined only for the region, it is defined in the region only where J is 0. The magnetic scalar potential is defined only in the region where J is 0. So this is the first definition, that is the magnetic scalar potential. Now we will derive the magnetic vector potential. So for that we will compare this divergence of curl of vector and the divergence of this vector B. So on comparing, equation 1 and 4, we get vector B is equal to curl of V. Okay, and instead of V I am using A. So this vector A is known as magnetic vector potential. This is called magnetic vector potential. Now this magnetic vector potential we can write in some different way also. The magnetic vector potential, if you compare the potential is written in the form of kq by r. So kq by r in case of electrostatic, so this is 1 upon 4 pi epsilon naught k, q is the charge, so this is dq, and divided by r is the distance and integration over the complete charge. So this is the potential that is written in the electrostatic. So on comparing with this, we can write the potential, this magnetic vector potential in case of magnetostatic. So this is vector A is equal to integration, this is the constant used in magnetostatic, which is mu naught upon 4 pi, like 1 upon 4 pi epsilon naught. Similarly, we have mu naught upon 4 pi, and here we have the current element IDL divided by the distance r. This is for the line current, that is a single conductor. Okay, similarly, we can write this vector A integration mu naught upon 4 pi, you can write k ds upon r. This is because of surface current. And there is another equation which we can write, which is mu naught upon 4 pi j dV upon r. This is for volume current density. So this is the potential that we can write in case of magnetostatic, that is the magnetic vector potential, in case of different line distribution, current distribution like line current, surface current and volume current. So now we will write some, we will solve few examples and we will write some formula also. So we have one example based on magnetic vector potential. So with the help of magnetic vector potential, we can calculate the flux. So in this example, we are having the magnetic vector potential whose unit is Weber per meter, and we want to calculate the flux passing through the surface. Phi is equal to pi by 2, rho is varying from 1 to 2 and z is varying from 0 to 5. So before the magnetic vector potential, if we want to calculate the flux, so the formula for the flux that we have studied is xi is equal to integration over the surface b dot ds. That was the formula that we were using before the magnetic vector potential to calculate the flux. But now we have another formula to calculate the flux, that is integration over the closed loop A dot dl. So here also we can calculate the flux. As you can see that this is having the unit Weber per meter. If you multiply it with meter, that is means some length, you will get the magnetic flux, which is having the unit Weber. So to calculate the flux, we can calculate B, or we can directly integrate this A dot dl integration over the closed loop. So here the surface we have to select, that is the phi is pi by 2. So that means phi is constant. So which surface we have to select? So if the phi is constant, as I told you, whatever the surface is given to you, if which parameter is constant, we will take the surface in that particular direction. So if the phi is equal to pi by 2, we will select the differential surface in the direction of phi. So in the direction of phi, that means the unit vector should be a phi. So what will be the other parameter? That is d rho and dz. That will be the differential surface. And that differential surface we have got, and this B we can achieve with the help of magnetic vector potential. This B we can get as curl of A. So this is the one method to calculate the flux, and for that we should have this B and ds, and this B and ds we can calculate from here. So let's calculate this B. So we are using first method, and in first method we are going to calculate curl of A in cylindrical coordinate system. So 1 upon rho, this is A rho cap, rho A phi and AZ del upon del rho, del upon del phi, del upon del z. This is 0, and this is minus rho square by 4. So we have 1 upon rho. Now A rho. So A rho, del upon del phi of rho square by 4 with minus sign, minus rho A phi, minus rho A phi, del upon del rho of minus rho square by 4, and Az we will be having 0. So differentiation of minus rho square by 4 with respect to phi, that is also 0. So here this minus and minus will become plus, and this rho and rho will get cancelled. So we will get the rho square by 4, and the differentiation of del upon del rho. Okay, so we get del upon del rho, rho square by 4. So you will get rho by 2. And yes, the unit vector is A phi. Okay, so this term will be 0, this term is 0, and 1 upon rho, and this rho will get cancelled, this minus minus become plus, this unit vector A phi will be having del upon del rho of rho square by 4, which will give you rho by 2. So this is the way we have got the B. Now we will calculate the flux xi is equal to integration over the surface. The B is rho by 2 A phi, and this is A phi d rho dz. So the dot product of A phi and A phi is 1, and double integration we are having rho by 2 d rho dz. So here we have rho is equal to varying from 1 to 2, and z is varying from 0 to 5. When we solve this, we get rho square by 4, and we get 1 to 2, and it is z. We have 0 to 5. After solving this, we will be having 4 minus 1 divided by 4 into 5. So this is 15 by 4 minus 1 is 3, and 5 into 3, 15 by 4. 15 by 4 is 3.75 Weber. So in this way you can calculate the flux. Now let's see another method to calculate this flux using the closed loop integration, and for that we should draw the closed loop, and according to the specification the closed loop will be formed in which plane? Phi equal to pi by 2 plane. So phi equal to pi by 2 you will get at because the phi means azimuthal angle, and azimuthal angle means the angle measured from the x-axis, and when we know that the angle between the x and y coordinate is pi by 2. So when you start from x, the phi will be 0, and when you reach to the y, the phi will be pi by 2. So in this particular plane phi equal to pi by 2, we will draw the loop, and the loop is like this. It is given that here the rho is 1, rho is 1 to 2, and the z is 0 here, and the z is 5. Now the magnetic field, the direction of the loop, what should be the direction of the loop? Because the surface is phi equal to pi by 2. Since the surface is phi equal to pi by 2, that means the value of phi is increasing. Phi equal to 0 to pi by 2, that means the value of phi is increasing. So we should take the direction of differential surface in the positive phi direction, as we consider here also the differential surface has the direction plus a phi. So here also the direction should be plus a phi. So for that we should have the magnetic field in that particular direction, and to have the magnetic field in the plus phi direction, and the plus phi direction is actually inside the board, because when we move from x to y, it is going inside the board. As we move in the anti-clockwise direction, we are moving towards the y-axis, that means inside the board we are moving. So for that the direction of current in this particular loop is clockwise. because when it is clockwise, the thumb will be pointing inside. So in that particular case, we will be having the direction of loop should be in the clockwise direction, so that the magnetic field will also inside the board and the surface is also inside the board. So we will get the same direction. So this is A, B, C and D suppose. Now we want to calculate integration over the closed loop A dot dl. And this loop is having the path like this, rotation like this. So we will be having from A to B, A dot dl, B to C, A dot dl, C to D, A dot dl, and D to A, A dot dl. So in A to B, the direction of differential length is this, which is plus y direction, and the direction of unit vector A is in the plus z direction. So here the angle is 90 degree. The direction of A to B is y, or you can say rho, okay, because here the parameter rho is changing from 1 to 2, that means that is changing. So for the A to B, for segment A to B, let me write once, for segment AB, the differential length, if I write d rho a rho cap, because when we move from A to B, the rho is changing from 1 to 2, that means the radius is changing, so the differential length will be a rho. Now the vector A is minus rho square by 4 az. So if we take the dot product of A dot dl, so it will be 0. Okay. This is for the segment AB. Now similarly for segment CD, if I calculate, here also the differential length is d rho a rho cap, because when I move from C to D, here also the radius is changing. Even we are moving in the negative direction, and we know that in case of differential length, we always assume the positive direction, and the direction of the differential length is compensated by limit of integration. So here also the differential length is in the direction of arrow. So again we get A dot dl equal to 0, because of A is in the direction of positive Z. Now for segment BC, differential length is, because when we are moving from B to C, the parameter Z is varying, Z is 5 to 0. So here the dl is dz az. Now if I calculate A dot dl, integration over B to C, I get B to C A dot dl. This is vector A, az dot az is 1. So we get minus rho square by 4 dz. And in this particular case, when we are moving from B to C, the value of rho is constant to 2. At every point in BC, the value of rho is 2. So this is 2 square, that is 4. 4 divided by 4 is 1. So here we get minus 1. Okay. And the integration dz, that means we get z. And from B to C, the z is varying from 5 to 0. So 5 to 0, that means we get 5. 0 minus 5 multiplied with minus 1. So this integration is 5. Now for segment, the last segment DA, for segment DA, here also the differential length is dz az, because when we are moving from D to A, you can see D to A, this parameter z is varying from 0 to 5, and this is having the constant value rho equal to 1. Now integration D to A dot dl is equal to D to A, the value of z is 0 and this is 5. A dot dl we get minus rho square by 4 dz at rho equal to 1, because in D2A the value of rho is constant to 1. At every point of the line DA the value of rho is 1. So if I substitute it, I will get minus 1 by 4, and if I integrate, I will get z 0 to 5. So here I will get minus 5 by 4. So now I have all the 4 result, A to B, this is C to D, this is BC, and this is DA. All the 4 integration we have got, this 4 integration we have got. So now we can write flux is equal to integration over the closed loop A dot dl is sum of all these 4, and we get 5 minus 5 by 4. So this is nothing but 15 by 4, which is equal to 3.75 Weber. So xi is equal to 3.75 Weber, which we have got using this method also. So in both the case we have got the same result. So in any formula, using any formula, you can calculate the flux, whether you use from B dot ds or A dot dl. So now next topic is magnetic boundary condition. So electric boundary condition we have studied. So we know that when the boundary condition is used, so whenever we have the field in one region and we want to calculate the field in other region, we use the boundary condition, and the field that satisfies the condition at the interface which is separating the two different medium is known as boundary condition, that we already discussed. So let's derive the boundary condition for dielectric interface in case of magnetic field. So for this we are having one boundary, and this is medium 1 which is having the permeability mu r1, and this is medium 2 which is having the permeability mu r2. The field is moving from the medium 2 to medium 1 like this. This is the normal. So this is B2 vector and this is our B1 vector. So it will be having the two components. This is the first component which is B. This is the normal component because this is the normal to the interface. If this is medium 1 and this is medium 2, so if this is the interface which is separating the two medium, then the plane, the normal is having in this direction. If this is the plane, so the normal will be in this direction. So because this is the normal direction, so it is BN1 and this is BN1 and this is BT1, tangential component. Okay, that we have already considered in electric boundary condition as well. Now we are having this as the normal component of second region and this as the tangential component of second region. So we know that field must satisfy the Maxwell equation. So the Maxwell equation for the magnetostatic is that we know that B dot ds should be 0, integration over the closed surface. So for this we need a closed surface. So let's draw the closed surface, that is nothing but a pillbox. This is delta S, which is having the cross section delta S, and the height of this pillbox is h or delta h. This delta S tends to 0. Now B and ds. So this surface is having the normal component Bn1 and the area is delta S. So the B dot ds will be Bn1, the magnetic field having the normal component Bn1, and the direction is also in the same direction. So this is the direction ds vector. So Bn1 and ds both are in the same direction, so that's why the angle between them will be 0. So this is Bn1 and ds1 or ds cos 0. So Bn ds cos 0, that means we get Bn1 into ds. Now for this particular surface, here we are having the surface in this direction, okay, because this BT1 and this DS is in the perpendicular direction, both are normal to each other, so that's why BT1 dot DS will be 0. So that's why we have not written BT1 dot DS. And again here also we are having the tangential component in this direction and the direction of the surface in downward direction, so again that will form a 90-degree angle. So that's why it will not be considered with the tangential component of magnetic field, but the normal component is in upward direction and the surface is in the downward direction, so they are making an angle of 180 degree because both are opposite directions, so they are making 180 degree angle. So cos 180 degree means -1, so here we will be having minus Bn2 ds equal to 0. So from here we will get the first boundary condition, that is the normal component of magnetic flux density are same. So here we will write normal component of magnetic flux density in both medium are same. That is, or in other words, normal component of flux density are continuous across the boundary. Continuous across the boundary. Okay, so you should remember that what is the meaning of continuous, because there is no change in the normal component of magnetic flux density when it is moving from 2 to 1, that's why it is known as continuous. Now we know the relation between the normal component and magnetic flux density and magnetic field intensity, that is B is equal to mu H, mu R1 and Hn1 equal to mu naught mu R2 Hn2. So we can also write Hn1 divided by Hn2 equal to mu R2 divided by mu R1. So here we can say that the normal component of magnetic field intensity are not continuous or are discontinuous, we can say, are discontinuous across the boundary. Okay, now we are having another relationship, that is integration over the closed loop H dot dl is equal to current enclosed. This is another Maxwell equation that has to be satisfied in magnetostatic. Now again we are having the magnetic field like this. This is the normal component of magnetic field intensity. This is region 1. This is region 1, and this is the tangential component HT1, and this is the normal component in medium 2, and this is HT2, H2 vector. So this is medium 1 having the dielectric constant mu R1, and this is mu R2. Now we have to form a closed loop because we want to apply this particular Maxwell equation or Ampere's law, integration over the closed loop H dot dl should be equal to current enclosed. So for this the current should be considered. So what is the current? So let's say that this interface is having a current. This interface, because this is a infinite sheet, you can say the plane, you can say. So if the plane we are considering which is separating the two medium, so if the current is flowing through the plane, we can distribute it into infinite long conductors. We can say that it has been it is looking like this. The current is flowing uniformly through the sheet, so we can distribute like this, and it is having a K, surface current density. Surface current density. Now let's make this closed loop, because we want to cover the sheet, na? So we will draw a closed loop which is known as Amperian path. So the height of this closed loop is delta H and the width is, say, delta W. Now this height should be very small, because we want to cover the sheet only. We want to cover this infinite sheet or the interface only. So this width should be very close to the interface. So to make the loop close to the surface, the height should be very less. Now we will apply this equation, integration over the closed loop H dot dl. So for this, let's take this A, B, C, D and again A. So when we move from A to B, we are having the tangential component, and the differential length is also in the same direction. Let us say this is the path in which we are moving. So A to B, we are moving in the direction of A to B, and the tangential component is also in the same direction. So that means they are making the angle 0. So what we can write is H T1, and the total length we know. So this is delta W. Cos 0, that is 1. Now when we move from B to C, it is divided into two parts. In B2, this interface, we are having the normal component of magnetic field intensity, and when we move from the interface to point C, we are having again the normal component of magnetic field intensity, but in the second medium. So we are having two different components. So, and this is in the downward direction, and the normal component of magnetic field intensity in upward direction. So both the vectors are in opposite direction. So if both the vectors are in opposite direction, they will form an angle 180 degree. So 180 degree means cos 180 degree minus 1. So that's why we will write minus of Hn1, okay, the first magnetic field intensity for the half of the height. So delta H by 2, because this is symmetrical about this interface, and minus Hn2 and again half of the interface delta H by 2. Now we will move from the C to D. So C to D, we are moving in this direction, and the tangential component of magnetic field intensity in D to C direction. So it is in this direction, and we are moving from C to D. So again these two vectors are opposite to each other. So these two vectors are opposite to each other means angle they will form is 180 degree, and because of cos 180 degree it is minus 1. So again there is a minus sign. Now ST2, and the total length from C to D is delta W. Now when we move from D to A, again this is the half portion in which we are in the second region. So in the second region we are having Hn2, but the direction of Hn2 and D to A is same. So that's why this time it would be positive. So Hn2 delta H by 2, and again Hn1 delta H by 2. This is equal to, this is all about the left hand side, that is integration over the closed loop H dot dl. Now the current enclosed. So how much current this particular loop is enclosing? So this is surface current density, which is defined in ampere per meter. So we have to multiply it with the length of the loop, and the length of the loop is delta W. So this is K into delta W. This is the current, ampere per meter into length, we will get the current. Now we know that this delta H, the height should be tending to 0, because this Amperian path should be close to the interface. So delta H will be 0. So if delta H will be 0, this term and this 4 term will be 0. So we will get HT1 delta W minus HT2 delta W is equal to K into delta W. So here we get HT1 minus HT2 equal to this K. So this is the second boundary condition. If K is 0, that means if the sheet is not having any current, if K is equal to 0, the HT1 is also equal to HT2. That means we will say that that is also continuous across the boundary. Magnetic field intensity, the tangential component of magnetic field intensity will also be continuous across the boundary if K is 0. And from here you can calculate BT. T1 divided by mu1 is equal to BT2 divided by mu2. So we can say that the tangential component of magnetic flux density is discontinuous across the boundary. It is continuous and it is discontinuous across the boundary. Okay. So suppose I consider they are making an angle. Suppose this is making an angle theta 1 and this is making an angle theta 2. So this is also theta 2. So if you want to write this H2, the cos component and the sine component, so we can write HT2 is equal to H2. This is the sine component, which is sine theta 2. And similarly H and 2 we can write cos component cos theta 2. If I divide it, I will get tan theta 2 equal to HT2 divided by HN2. Okay. Similarly, if I write it from this above equation, here I will get the HN1 as the cos component and HT1 as the sine component. Again, we will get HT2 is HT1 this time, because we are writing in the first medium. So this is sine theta 1 and HN1 is equal to H1 cos theta 1. Normal component is in the cos component. So if I divide it again, I will get tan theta 1 is equal to HT1 divided by HN1. Now we know that the tangential component are equal. So if I divide these two equations, I will get tan theta 1 divided by tan theta 2. So we will be having HT1 divided by HN1 multiplied with HT2 divided by HN2. The tangential component are equal, so they will get cancelled. According to the boundary condition, if K is 0, these two components are equal, so we will get this will get cancelled, and this relation Hn1 can be written as Bn2, Hn equal to mu naught mu r2, and Bn1 Hn1 can be written as Bn1 mu naught mu r1. So this normal component is also equal. The normal component of magnetic flux density from this boundary condition, Bn1 is equal to Bn2. So this Bn1 and Bn2 will also get cancelled, and this mu naught and mu naught will get cancelled, and finally we will get tan theta 1 divided by tan theta 2 is equal to mu r1 divided by mu r2. So this is the relation between the angles. Same relation we have got for the electric boundary condition, but there was the parameter that was associated with these angles was permittivity, relative permittivity. So this is the magnetic boundary condition, and we will be solving the workbook questions related to this particular topic. So next topic is magnetic force. So magnetic force we will calculate in three different cases. First we will calculate in the charged particle. Second, we will calculate the force on a current element, and third, we will calculate the magnetic force between the two current elements. Okay, so I will write it here. The first, force on a charged particle. second force on a current element, all because of magnetic field, okay, because we are dealing with the magnetostatic chapter. And third is force between two current elements. So this is the three different cases that we are going to study. So first is, let's say, force on a charged particle. So force on a charged particle we can calculate in case of electrostatic as well, because the electrostatic, we know that whether the charge is stationary or moving, if it comes in presence of a electric field, it will experience a force, and that force is given by Q into E. So when a charge is stationary or moving in electric field, if a charge is stationary or moving in electric field, it experiences a force, a electric force, and this force is given by Fe is equal to the charge Q and the electric field intensity. This is because of the electric field. If a charge is moving, charge cannot be stationary in case of magnetic field. Okay, so if a charge is moving with velocity v in magnetic field, it experiences a force, a magnetic force, and that is given by Fm is equal to Q into V cross B. If a charge is moving with velocity v, if a charge Q, okay, if a charge Q is moving with velocity v in magnetic field B, then it experiences a force. That charge will experience a force, and that force is given by Q V cross B. And similarly, if a charge Q is stationary or moving with in electric field E, then it is experiencing a force A Q into E. So this is first equation and this is second equation. In both the fields, if I say both the fields, let us say both the fields, electric field and magnetic field, are present. So if both the fields are present, then the force is sum of Fe plus Fm. That is the force because of electric field and magnetic field. So this force, the net force, is given by Q into E plus Q into V cross B, or we can write F is equal to Q is common, we can write E plus V cross B. So this is the force equation which we have got in case of a charged particle, and this is known as Lorentz force equation. So sometimes directly this type of question is asked, which one of the following is a Lorentz force equation? So this should be the answer. Okay. Now I can write in the form of table. The electric force, magnetic force, charged particle, first case is stationary and second case is moving. So if a charged particle is stationary or moving, let me write like this only. Stationary. If a charged particle is stationary, then it will experience a force QE and there will be no magnetic force on that stationary charged particle. If the charged particle is moving, then also it will experience a force QE, but in case of the moving charge, the magnetic field, magnetic force will also be present and it will be V cross B. You can write like this in the form of a table. Okay, now the second case, force on a current element. Suppose this is the current carrying conductor, and in this current carrying conductor, this is the current element ideal. So because of some magnetic field, because of there is some any other current distribution, and that current distribution produces some magnetic field, and because of that magnetic field, this current element experience some force. And what is that force? So because of the magnetic field which is produced by any other current distribution, the force on this particular current element, so due to magnetic field produced by any other current element, any other current distribution, force on current element, force on this particular current element. Okay, because we know that if this is the conductor and it is having some current, then it will also produce some magnetic field, but that magnetic field is not responsible for the force that this current element is exerting. Okay, so this current element is experiencing a force because of the magnetic field produced by some other current distribution. So this force is given by I dl cross B. I dl cross B. I dl cross B. This IDL and the B is because of some other current distribution which is producing a magnetic field at this location. Now the third one, force between two current elements. So we are having, suppose, two different configurations, conductor. So like this, we are having a conductor. So this is the positive terminal, this is negative terminal, so current will flow like this. So this is I1, and suppose somewhere here we are considering this one is I dl1, I1 dl1, and the current is flowing through this loop like this. Now there is another positive and negative terminal, and it is placed like this. So it is having a current I2, it is flowing like this, and let us say here we are having one current element which is I2 dl2. Now these two current elements experience a force into each other. So for that, because of this current element, there will be some magnetic field in this location where this current element is selected. We have selected the current element here. It is at distance, suppose this is 2 and this is 1. So we are line joining from 2 to 1. So let it be R to 1. We are line joining from 2 to 1. So because of this current element, because this is the conductor in which the current is flowing, because of this current element, some magnetic field will be produced. That is the differential magnetic field, and that magnetic field exert the force into this particular current element according to this formula. Okay, because we are saying that this IDL cross B, that means this B is the magnetic field produced by some other distribution. So here we are having one current element and here we are having some current distribution, and because of this current distribution we are having some magnetic field at this location. So in this location, this particular current element will exert some force, that will experience some force. Okay, so what is that force? So we will write it as D into D F1, d df1. I am denoting it by d df1. Why it is so? Because of this small current element we will get small magnetic field, and that small magnetic field experience exerting a force into small current element. So this is the small current element. So there are two different small thing we are using, or differential thing we are using. First, differential magnetic field because of the differential current element. Second, small force on this small current element. Now this current distribution will exert a force in the complete conductor. So for that we have to integrate over the length of this conductor, and this complete conductor will experience more magnetic field, and for that magnetic field we will integrate along this particular conductor, length of the conductor. So that's why there are two differential. I am using D and D. So this is I1 DL1 cross P2, this B2, this current element which is having some magnetic field, dB2 you can write. So what is that dB2? This dB2 is from the Biot-Savart's law, current element, because of current element what is the magnetic field? So this is mu naught by 4 pi I2 DL2 cross from 2 to 1. So that is unit vector in the direction of 2 to 1 divided by R21 square. Now I will substitute this magnetic field into this equation, then I will get D dF1. This is the force. Force is also a vector quantity. I1 DL1 cross this mu naught upon 4 pi I2 DL2 cross AR21 cap divided by R21 square. Now to get the total force, on this complete current element to complete conductor, now to get the total force on this complete conductor, we have to integrate along the length of this conductor and this conductor both. So that's why we will be having F1 is equal to mu naught upon 4 pi I1 into I2 divided by R21 square, integration over the complete loop along the L1 and L2. We will be having DL1 cross DL2, let it be R21 square and AR21 cap. So this is the total force that is experienced by the first conductor due to the magnetic field produced by second conductor. So we have to integrate along the first length of the conductor and second length of the conductor. So I1, I2 is independent of length, mu naught upon 4 pi is constant, so they are all common, and inside the integration this will be the term. So this is the force between two current elements. Now because this is the force which we are getting, you can also calculate the direction of the force, because the force is a vector quantity. So the direction of force you will get. So what will be the direction of force? So direction of force you can calculate from the left hand rule, Fleming's left hand rule. So I am using this Fleming left hand rule for direction of force. So according to this left hand rule, this is how I have drawn. This is the left hand, this is the index finger, this is middle finger, and this is thumb. So if the middle finger is in the direction of current, middle finger, this is index finger or forefinger, and this is thumb. So what we are saying is, if middle finger denotes the direction of flow of current and the index finger denotes the direction of magnetic field, then the thumb will be pointing the direction of force. Okay, so this thing you can see in this particular case. If we are having two straight conductors having a current I1 and I2, suppose, or let's say the same current. Okay. Now because of this current carrying conductor, using the right hand rule, I can say that the magnetic field will be around this conductor, because this is the simple conductor and this is the infinite long straight conductor, and the current is flowing in the upward direction. Then finger encircling this conductor will be the direction of magnetic field. So the direction of magnetic field is encircling this conductor. So because of that, if I apply the right hand rule to get the direction of magnetic field on this particular conductor, which is having some distance, let us say the distance between these two is d. So this particular conductor will will generate some magnetic field in this particular location, and let us say here the magnetic field is cross. Obviously it is inside the board, so it is denoted by cross. So the direction of magnetic field in this particular conductor is inside the board and the flow of current is upward. So we are having these two things. The middle finger will be showing the current and the magnetic field. So we are having these two things here. This is B1 because of the first conductor. Okay. Now we have to apply the Fleming left hand rule in such a way, then the middle finger should be in the direction of flow of current. So this is denoting the direction of flow of current, but like suppose if I denote like this, then can we show this particular case? See, this middle finger is in upward direction. You can see from here, the middle finger is in upward direction and this index finger is inside the board, because index finger should be showing the direction of magnetic field. So we have to point the index finger inside the board so that it matches with the magnetic field. So this is inside the board, and in this case this is the direction of current. So the thumb is pointing towards left. You can see again, this is the direction of current in upward direction. Index finger is inside the board and thumb is pointing in left hand side. So this is the direction of force here. So this particular conductor will experience force in the left hand side. So this is the direction of force. Now because of this straight conductor, there will be some magnetic field here also, because this is infinite long conductor and the current is flowing through this conductor. So it will also generate some magnetic field around this. So this particular conductor will also experience some force. So that particular force, that particular magnetic field that will generate here is outside the board. So here outside the board. So outside the board means it will be represented by dot. So this is the magnetic field B2 because of the second conductor. So this is the how we have applied the right hand rule, because the point is located in the left hand side. So this will be the fingertip, and that is coming outside the board. So this is the outside the board, right? Now again we have to apply the same thing. So now see, this is the case. So this is the case because the index finger should be pointing outside the board and the direction of flow of current is still upward. So it is still, the middle finger should be pointing in upward direction and this is pointing in outside the board. So you can see that here. So the thumb is pointing in the left hand side now again. So here it is now pointing in the right hand side from this side. You can see that it is now pointing in the right hand side. So here it will experience 4 in this direction. So we can say that if there are two parallel conductors and if there are two parallel conductors and the current is flowing in the same direction, then they will attract each other. You can see that the force this will experience on this particular conductor is towards the conductor, and that is also same for this conductor as well. So these two are attracting each other. So we have studied in our class 12th also, if there are two parallel conductors, so they will attract each other if the current direction is same in these two conductors. So the direction of flow of current is same, that's why they are attracting each other. If you will find this case, the direction of flow of current is opposite, then you will find that the direction of force will be in this direction because of this, and it is in this direction. You can find it and you will get this result only. This is cross, and for this if I apply the right hand rule, so it is for cross for this also. This is the direction of magnetic field, and according to the magnetic field and direction of current, you will find the direction of force in the left hand side and the right hand side. That is, they are repelling each other. You can do it by your own. So this is all about the magnetic force. So two parallel wires current flowing in the same direction, they will attract each other. Two parallel wires, current is flowing in the opposite direction, they will repel each other. So next topic is inductance. So here I have written how can we define the inductance. For inductance, what is the basic requirement? Suppose there is a closed circuit and the current is flowing through it. So if there is a current flowing through the conductor, then the magnetic field will generate, and the magnetic field is responsible for a magnetic flux. So this magnetic flux, if it links with the number of turns, then it will called as magnetic flux linkage. When the magnetic flux link with number of turns, then it is called as magnetic flux linkage. So the magnetic flux linkage, how you can define? So it is defined as the total magnetic flux linking in a given circuit or conducting structure. The magnetic flux linking with linking in a given circuit or conducting structure. If the structure consists of many loops, single conductor with multiple loops, that is in case of solenoid. If we are having a long conductor, that is a straight conductor or finite length conductor, and if we make multiple loops, then it will be having n number of turns. So when the magnetic flux linking with this particular number of turns, it is called the magnetic flux linkage. So the magnetic flux linkage, here we can define this lambda is equal to n, that is the number of turns, and xi. Okay, so where n is number of turns and xi is magnetic flux and lambda is flux linkage. Now, as we increase the value of current in the circuit, the magnetic field will also increase, because we know that in any case the magnetic field intensity in any current distribution is directly proportional to the current. Suppose you talk about the infinite long current carrying conductor, then the magnetic field intensity is given by I upon 2 pi rho. So that is also proportional to the current. So whatever we have derived till now, we have seen that in all the case the magnetic field is directly proportional to the current. So if you increase the flow of current in the circuit, the magnetic field will also increase. So magnetic field will increase and the flux will also increase, because the flux is equal to B dot ds. So if the magnetic field increase, the B will increase, that means the flux will increase. If the number of flux will increase or the flux increase, the linkage with the number of turns will also be increasing. So you can say that the lambda is actually the flux linkage is proportional to the current, because as you are increasing the current, field is increasing the flux is increasing the flux linkage. So this proportionality, we are using a constant, you can say L, that is denoted by inductance. So this is L is equal to lambda by I. This is how we calculate the inductance. This is the self inductance, because it is responsible and it is generating by its own structure. So there is no interaction between the two different structure. This is a single conductor that is producing a magnetic flux, and the linkage is also produced by that magnetic flux only. So that's why it is known as self inductance. Lambda is equal to N into xi by I. So this is the value of inductance. That is very, very simple. Now, in case of solenoid, we have calculated the value of H. The value of H is N into I divided by L. So the value of B we can write is mu into H. So this is mu naught Ni upon L. Now the flux is xi is equal to B into area, where this A is the cross section area of solenoid. So how can you write the inductance? So the inductance is L is equal to N into B into A divided by I, because xi is equal to B into A. So B into A is xi and this is N upon I. So N B A upon I. The value of B we have already written for the solenoid. We are saying about the solenoid right now. Mu naught Ni upon L, that is the value of B that we have substituted here. The value of I and I will get cancelled and we get N square mu naught A upon L. So the value of inductance for solenoid is, if I rearrange it, mu naught N square A by L. For solenoid. This is very important. Okay, so similarly you can calculate for any type of structure like toroid also. Suppose I want to calculate, let us take one example. This is the infinite long current carrying conductor and there is a square loop. This is the square loop. Which is at distance B from the infinite long current carrying conductor. Now you have to find the mutual inductance between these two. So there are two different structures, that's why we will call it as mutual inductance. The formula will remain same. So the formula will be same, and because this loop is having the one number of turns, so the formula will be from N xi by I. The number of turn is 1, xi is B into integration B dot ds, okay, and divided by current I. This is, now we will call it as mutual inductance. This is here is mutual inductance, which is actually denoted by M. So because there are two different structure, that's why we are calling it as mutual inductance. Okay. Now what is the value of B here? So because of this is having the current, this conductor is having the current I. So that's why this will generate the magnetic field, and the magnetic field lines will pass through some surface, then it generates magnetic flux. So here the magnetic field will generate here also, but it is not passing through any surface. The magnetic field will be generating here also, but they are not passing through any surface, so they will not contribute any flux. But when the magnetic field line will pass through this particular surface, then it will produce some flux. So let us say we want to calculate the flux passing through this small length dx. This is along the x-axis, suppose. This is suppose x-axis. So we are saying that when it is passing through this, let us say this is passing through dx. So flux passing through differential area we can write d xi is equal to b into dA dash, let us say area, very small area. So what is this value of area? So area of this strip is dx, this is a small length dx, and the height is a. So the value will be a into dx. So now to calculate the total flux, we have to integrate it over the surface. So we have got this, the total flux will be integration over the x, b into a into dx. We have to integrate this, and the value of B we know, because this is infinite long current carrying conductor. The value of magnetic field will be, because of the infinite long current carrying conductor, this is mu naught I upon 2 pi x at any distance x. If this is this strip is at any distance x, we want to calculate the magnetic field at this location dx. So the magnetic field, that is B, which is at this location, will be B is equal to mu naught I upon 2 pi x. So this is mu naught I a upon 2 pi x into dx. Now to cover the, or to find the complete flux or the total flux passing through this particular square loop, the value of x will be, x is here B, it is starting from B, and here it is B, and this length is A. So this is A plus B. So x is varying from B to A plus B. So here x is varying from B to A plus B. Now xi is equal to mu naught I a upon 2 pi is constant, and 1 upon x is natural log of x, and when we substitute this b, limit b to e plus a, we will get mu naught I a upon 2 pi ln a plus b divided by b. So this is xi, and this is mu naught I upon a, and we know that number of turns is 1, so this is actually equal to xi by I. So xi by I will give you the mutual inductance. So this I, if I divide it by I, so this will be xi by I, that is the mutual inductance, and the value will be mu naught a upon 2 pi ln a plus b upon b. So this is the formula of mutual inductance in this present structure. Okay. So if you are having the structure like this, then this will be the value of inductance, and this question has been asked in GATE 2020. Okay, so the value of A, B is given to you in the question. You can directly substitute these values, and you can find the mutual inductance. Or if you want to derive, because if you don't know the formula, you want to derive it, you can derive it in this way. So to derive the mutual inductance, there should be two different structure, and you can use this formula. And if there is only single structure, then you can directly use this formula. And for solenoid, you have to remember this formula, because this formula has been asked many times in the past years. So next topic is Faraday's law. This law is very, very important. Suppose there is a static magnetic field, then there will be no flow of current. static magnetic field produces no flow of current. Okay, but if I talk about the time varying field, that is the magnetic field that is changing with respect to time, then it causes a flow of current in a closed circuit. So because of this flow of current, there will be again a magnetic field, and which produces a induced EMF. Okay, so you can write it down. I am telling you. So according to the Faraday's experiment, a static magnetic field produces no flow of current. Please write. According to the Faraday's experiment, a static magnetic field produces no flow of current. But in a closed circuit, a time varying magnetic field produces an induced voltage. Time varying magnetic field produces induced voltage, which causes a flow of current. So Faraday's law, it states that, after writing this, please write this one. It states that induced EMF is equal to time rate of change of flux linkage. Please write this. It states that induced EMF in any closed circuit is equal to the time rate of change of magnetic flux linkage by the circuit. It states that induced EMF in a closed circuit is equal to the time rate of change of flux linkage by the circuit. So according to this, induced EMF is equal to minus of n times of you can write like this, minus of d lambda upon dt. The flux linkage is lambda, time rate of change of flux linkage, and we know that the lambda is equal to n into xi. So minus del upon del t, this is n into psi. So this is the Faraday's law. Now what this minus sign indicates? So this minus sign indicates that this induced EMF opposes the flux producing it, because this time varying flux is responsible for the EMF. So this minus sign denotes the induced EMF is in such a way that it opposes the flux producing it. You can write that also. The negative sign shows that induced voltage acts in such a way so as to oppose the flux producing it. Negative sign indicates that voltage or EMF produced in such a way as to oppose flux producing it. Now actually this negative sign is defined by the Lenge's law. The importance of this negative sign is defined by this Lenge's law. So what is this Lenge's law? So it emphasizes that, you can write that, it emphasizes that the direction of flow of current, the direction of flow of current in a loop in the circuit, the direction of flow of current in the loop or circuit is such that induced magnetic field produced by induced current. It emphasizes that the flow of current in the closed circuit or loop is such that induced magnetic field produced by induced current will oppose the change in original magnetic field. Okay, let me write it for you. It emphasizes that direction of flow of current in a circuit or loop is in such a way that induced magnetic field produced by induced current, because there is a EMF, so because of that EMF the current will flow. So the direction of current, how do you define the direction of current? So the direction of current is in such a way that induced magnetic field produced by induced current will oppose the change in original magnetic field. Change in original magnetic field. So this is the Lenge's law. Okay, so this is the Faraday's law. Now we will study the Faraday's law in three different cases. First is the loop is stationary. Second is the loop is moving but the field is stationary. And third is loop and the field both are varying. The loop is also moving and the field is also changing with respect to time. So first case, when the loop is stationary, so this case is known as the transformer EMF. So how can we define this? So we know that this EMF is produced in the closed loop is E dot dl, or the voltage produced in a closed loop is E dot dl in case of electrostatic. Here we are saying that this induced EMF is minus of N into del xi by del t, or we can also write this minus N del upon del t, this integration over the surface B dot ds. Both are saying that this is voltage on the in a circuit. So these two equations should be same. So if this two equation is same, that is integration over the closed loop E dot dl, both are representing a voltage. That's why these two equations are same. So minus N del upon del t, integration over the surface B dot ds. The number of turn is 1, obviously in a circuit, a single circuit which is having only one loop, so the number of turn is 1. So if I write in this way, if the number of turn is 1 for n equal to 1, okay, so this is integration E dot dl and minus del upon del t, integration over the surface B dot ds, or del B upon del t you can also write. So this is the Maxwell's equation that derived from the Faraday's law, that we have already seen in the integral form. The table we have already drawn. So Maxwell equation derived from the Faraday's law. So if there is a stationary loop or a circuit given stationary, then you can apply this formula, and the differential form of this we can also derive if we say that if we apply the Stokes theorem. Okay, so Stokes theorem says that integration over the closed loop A dot dl of any vector A is equal to integration over the surface, open surface, the curl of that vector A dot ds. So if we apply this case in our this integral form, so the left hand side will become integration over the surface curl of E dot ds, and the right hand side is minus del upon del t integration over the surface B dot ds. So on comparing, we get curl of E is equal to minus del B upon del T. So this is the Maxwell equation derived from the Faraday's law in differential form. That is also we have already written. So this is the case when the loop is stationary. Now suppose if the loop is moving, then how can we find the induced EMF? So next is second case, loop is moving in static field, static magnetic field, and this is called motional EMF. Okay, so loop is moving in static field. So suppose if a charge is moving in presence of electric field, then in presence of magnetic field, if a charge is moving, then the force is denoted by Fm is equal to Q into V cross B, right? So what is the electric field? So the motional electric field, this motional electric field, because to write the EMF we need E dot dl, because we know that V is equal to E dot dl. From here we can see that this is V is equal to E dot dl. So we need a electric field to write the EMF. So what is that EMF? The motional electric field is defined as EM is equal to the force per unit charge. So that is V cross B. So if the conducting loop is moving with velocity V, if conducting loop is moving with velocity V, as there are large number of free electrons, so we get the induced EMF is equal to integration E dot dl, that is EM dot dl over the closed loop. So this is integration over the closed loop, this is V cross B dot dl. Okay, now we can also define in terms of this is the closed loop, so we can also convert it into the surface integration. So it can also be written as surface integration curl of V cross B dot ds. Okay, so if we compare it with the integration over the closed loop E dot dl, if I convert it into the surface integration, that is this one, curl of E dot ds. So curl of E dot ds, if I write this particular case as the curl of E dot ds, then we can compare these two and we can say that the curl of E is equal to, if we compare these two, we get curl of E is equal to curl of V cross B. This is in the differential form. Okay. Now the third case is when the loop is moving in time varying field. So if we want to write EMF, then integration E dot dl, here we will be having minus del upon del t integration over the surface B dot ds, okay, plus integration over the closed loop. Because of the, this is for the stationary field, this is for the time varying field, and the second one is for the static field. So for static field, integration over the closed loop V cross B dot dl. So V cross B dot dl. So if the left hand side, this is integration over the closed loop, is converted into the surface integration, then how can we write this? So this is already in the surface integration, so minus del upon del t integration over the surface only, not a closed surface, only the surface, B dot ds, and this can be converted into the surface by curl of V cross B. So if we compare, we will get curl of E is equal to minus del B upon del T plus curl of V cross B. So this will be the formula, differential form of this EMF. Del cross E is equal to minus del B upon del T plus curl of V cross B if the loop is moving in the time varying field, and if the loop is moving in a static field, we will get the curl of EM, that is motional EMF, and curl of V cross B. So this is all about the chapter magnetostatic. Now we will solve workbook question based on the Faraday's law and the topic we have discussed, and then we will move to the next chapter.